Okay, welcome to our third R session. In this session, we are working on linear regression lines. Linear regression lines are one of the most famous topics in the statistics. Now we have to learn how to use R to implement those. One of the things that is necessary for this lecture is that you must make sure you have already installed the package ISLR. If you're connected to internet, then just write install packages and ISLR in quotation. If you find it and tries to install it, and something like this happens, tries to install it and it install it here. So I have it there. So now I can continue. You need two libraries here. So that's the first time you need libraries. And the first library is called library mass. And the second library that you need to use is library ISLR. So these are the two libraries we need. If you do not use these libraries, you cannot run your regression lines and you cannot use the Boston data that we are looking after now. So in this lecture, I'm going to use the Boston data. So let's see what Boston data is. Boston data is, as before, whenever you're not sure what you're looking after, just put a question mark before what you're looking after, and everything that you need will be shown to you. So Boston is a data frame which has 406 rows. That means it has 406 observations with 14 columns. That means it has 14 variables. It has per capita crime rate by town, and the value of the variable is called crime, or CRIM. Proportion of non-retail business acres per town, industry, indus, and as you can see, there are a lot of things that are here. So let's some of the most important ones: are median value of homes in $1,000. That is median F. And LSTAT is lower status of the population. That means LSTAT shall be a number between 0 and 100%. That means in that neighborhood, what percentage of population have lower status. And as we can see, that can usually affect this median value. As black has the percentage of African Americans in the neighborhood. PT ratio is pupil-teacher ratio, student-teacher ratio, and so on and so forth. So there are a lot of things for different neighborhoods here. And now let's see how we can see that. So the first thing we usually do when you want to understand the data is to plot it. So let's plot some of these values here. So let's plot median value versus LSTAT. And the data you need to find is Boston. This is you can read tilde as versus. So you want to plot median value versus LSTAT, and the data you're using is Boston. So Boston is the source of data here. Okay. So let's plot it and see what we see. Okay, my mistake, that's LSTAT, not. So we want to see how the median values will be changed by lower status neighborhoods. As you can see, the more lower status people that are living in that neighborhood, the lower the median value of that neighborhood. And it makes sense. If they can live there, that means it was cheaper, they could afford it. That's why the median value is less. And perhaps these Boston neighborhoods, which have very few lower stat neighbors in it, people in it, have high median value because it was perhaps way expensive for them to afford it to live here. So we see a relationship between the two. And the first thing we are going to try is simple linear regression line. Regression line. That is when you only have one variable and one output. So for example, we want to fit a line from LSTAT to median value. See what is the relation of these two variables, and that's the sole thing we're looking after. If you want to use a linear model, you use LM. If you're not comfortable what this function is, just ask what LM is. You say that's a linear model. You need to have your data, your subsets. If you have, for example, if you just divide your data into training and test data, then you can use this subset here. And formula means what are you regressing on what? You have one y variable and couple or just one independent variable. You should make sure you introduce that, and the rest of the things you usually don't use it. And the weight also is beyond the scope of this class. But it's not bad that we use weight in some of the cases. We had generalized or weighted least squares. That's a very nice and neat thing to deal with. But let's focus on the easiest case where we have a formula, we have some data set, and we have a subset of that to use. In this case, I'm running my regression line on all my data, so you don't have any subset. That's the easiest case you can have. So I want to regress median values on LSTAT, and the data we are going to use is called Boston, right? And our data source is Boston. I can say, okay, data is Boston. If you had training data, then you could add, for example, subset is equal to something. But here we didn't divide training and test data, so we just focus on that. So that's my first model. So anything regarding this linear model is saved in this fit1 model. So let's call this fit1 model and see what it has. So let's call it with summary. So summary gives you all the values that it has. Okay, that was fit1, not fit. So as you can see, the fit1 is a function of LSTAT, because that was one regressor. The coefficient was, let's say, minus 0.95, which says for every percentage of LSTAT we have, the value in $1,000 will decrease by minus 0.95. So it almost affects the price by $1,000 on average. And this is the intercept. The coefficient is very significant. The R square is 54%, and the p-value for model is very small, which is very promising. That means the model is okay. It's not the best model you can assume, but it's okay. So let me plot that again. Okay, these were our original thing. Now you want to plot that line and see how this line works. If you want to run a line, so plot regression line, what you need to do is to define it as AB line. That's how you define the line. Okay, you say, okay, use the fit1 model, and here you can just set its color, and you can do so many other things as well. But I just drew the line based on the fit1 model, and the color for that curve is red. One thing that you can easily see, and it's easily observable here, is that this relationship is not that linear. It shows a nonlinear relationship. The line did a good job, but that's not the best thing you could do. Okay. So the second thing you need to know is that, let's see, what do we have in fit1 model or any other fit1? If you want to do it, you use names. So the outcome will become coefficients, residuals, effects, rank, and so on and so forth. Later on, you can refer to them. Some of them is listed here above. Some of them are not. To be honest, usually when you have the summary, you get the things that are important. You don't need these values, okay? You might be interested to build confidence intervals for your coefficients. So confidence interval for your coefficients. And that's a very important thing, because usually the absolute values of the coefficients are not that important. What is important is that what is the in confidence interval for that. The command for that is conf int. There's confidence interval for your fit1 model. If you don't write anything else, that assumes that you're looking after 95% confidence interval, and it gives you the values. For instance, your prediction was minus 0.95 for L-stat coefficient, but the confidence interval will be from 95% confidence will be from minus 1.02 up to minus 0.87, which is significantly lower than 0, and that was why it was so significant. But you might be tempted to change that confidence interval to 99% confidence intervals. And if you want to do that, you just add another term at the end of this function, and that dictates the confidence interval you're looking after. So my fit1 confidence interval at 99%. Why does it show me that? It should give me... Okay, so let me put it in X. Let me ask it to give me back X. It's very weird. Okay, so conf int. Okay, let me say level equal to 0.99. Maybe that's how it understands it. Level equal to 0.99. X. Okay, now it works. Okay, so in order to fix the confidence interval, you just need to write the level equal to something. That's a very important distinction. As I said earlier, whenever you're not comfortable with the results you get and you're not comfortable with what that function is doing, just put its question mark before it and just read what it does. You see, I exactly the same thing. Level 95%, got it. It should be 99% now, and I fixed it. Okay, so please be comfortable using these question marks. Another thing you can do for regression lines is to use the predictions. In order to use the calculate the predictions, you should, again, let me call what prediction is. Predictions have different objects inside it, so you should say, okay, what object you're using, that's fit1, and what are the arguments of that. It didn't do a great job defining it, so I define it here. Here, so the predict function does the prediction job. The first element of that would be the model you have. The second thing you need to have is, what do you want to make predictions upon? For instance, you can have a test data or training data and just put it here. Okay, so if you have test data or training, you can just put it here. Or you can say, okay, I am interested to understand the values of my data for LSTAT if it is treated as 5, 10, and 15. So what you say here is that assume your LSTAT here is 5 or 10 or 15%. What is your prediction about the value of that? So that's what you want to find. Okay, so you can put here any data you want, but here I just created the data. But if you have created it before, like you have training data or test data, you can just put it here. And comma, you can define the confidence interval. Let me make sure the parentheses. Okay, so you should do it outside it. So we have the confidence interval, and the confidence level, we want to fix it to 99%. You can just set it to any number. So if you do that, it gives you the predictions for these 5 values at 99% confidence level. So please look at the bottom of the page. So for 5% lower status people in our population, our prediction is 29,080 for the median price, with 99% confidence interval that changes from 28,000 to 30,000. For 10% lower level income, our prediction is 25,000, and our confidence is this much, and so on and so forth. Okay, so that's basically what it gives you. As has been discussed in the class, the simple linear regression lines are not used that often. You usually are interested to plug your data upon way more variables. So let's try those as well. One of the things you can easily do is to add more variables to data, and that's pretty simple. You again use your linear model. You should define your response, which was our median value, and here let's keep it all a step because it was very significant. Let's add variable age. If you want to add something, you just put plus here. It's as simple as that. And our data is again Boston. So let's get the summary of our phi2. Our summary shows that age is significant, and our R squared before was 54.41%. Now it increased to 55.13. So it shows that the age, although it affected, it didn't add too much to our data. Again, our p-value is very small. Keep it that way. We might be interested to run our regression line on every single value. What should we do in that case? So if you're interested to run your regression line on every single value that is there, you just put a dot here. So you say regress median value on everything. That means every variable that is there, and our data is again Boston. So let's get the summary of our phi3. Our summary shows that age is, when you run it on all of the variables here, age is no longer significant. Neither industrial zone percentage. So we can drop these two variables and retest our data. One of the ways that you can do that is just put a negative sign. So whenever you want to add a variable, you just put add here, plus here. If you want to subtract a variable, you just put negative sign there. So let's have our fourth model has everything but the variables that are not desirable, such as age and industry. Oh, what did I do? Oh, I didn't define data point. So data was Boston. Let me see. Oh, that was median value. Perfect. So summary phi4 in this case would become this, and as you can see, everything is very significant now. An R squared from 50% increased to 74%. So our model improved a lot. Some of the things you may do in addition to these changes might be you might want to have some nonlinear transformations, or you want to add interaction effects. So how should we do that? So I will start with adding interaction effects. So let's add LStat age interaction effect. So if you want to add an interaction effect, it's pretty simple. You just use your linear model again, median value on. Let's say I'm just interested to see the interaction of LStat and age. What am I doing? LStat, okay, my data is Boston. I always forget this part. So summary of phi5 will become this. That says the interaction effect is significant at 2.5% level. although age itself was not significant. So if you have such a model, the interaction effect is a significant. Age is not, you cannot drop age anymore if you want to have this interaction effect there. But fortunately, this interaction effect is not that, the magnitude of this interaction effect, which is 0.004, is very small, because L-stat was between 0 and 100, and age is between, I think, up to 50. So even for the, and I didn't see any L-stat more than 30, to be honest with you, in the data. So even if L-stat is 30 and age is 50, that's 1500. That would, for large values of L-stat and age, that interaction effect is very significant. So we should keep that. So the conclusion we get is we should keep it here. So you may be interested to go slightly further and try more degrees of polynomial in your linear model. For instance, let's get back to the plot we had earlier. This plot was very nonlinear. So let's say you're interested to apply more nonlinear cases on your L-stat. So you want to have L-stat, L-stat squared, and so on and so forth. There are actually two ways to deal with that. One way is just, let me call it fit 6. It's a linear model of median value versus L-stat. And if you want to add more different functions, you just put I and write the formula you want on top of it, L-stat squared, and your data is Boston, right? Another way you can do that is, so let's see first what this fit 6 is giving us. Yeah, two values are very significant. Another way you can do the same thing, it would be to use a function called poly. So fit 7 is LM mid value, and instead of writing LSAT plus I LSAT squared plus I LSAT 3, I just write poly. That means use a polynomial of LStat up to 2 degrees. You can change it to any value you're comfortable. So let me start with 2 to show you that that gives you exactly the same outcome as before, to summary fit 7. So this is 64, this is minus 1.52. Okay, so I think I screwed somewhere. Okay, it's strange. I got different values for polyStat. And strangely, their R squares are the same thing. Okay. That is slightly strange. Let me... That was fit 5. Okay, so I have to see what poly does. Yeah, it goes up to degrees of 5. What is poly M? So let me try poly M for fit 7. Okay, it doesn't understand that. Okay, I only have one explanation for that. Since we get exactly the same amount of R squared, the only explanation I have is that, yeah, we get the same R squared here. Okay, the only explanation I have is that it has more than one minimizer here. Sometimes when you want to minimize your least square functions, it may have more than one values, and that's when your matrices have the eigenvalues that is not that is one less than the eigenvalues of the inverses of the matrices times itself. So it may happen, but they essentially created the same level of data, so it has multiple answers. So the second degree polynomial have multiple answers, and they both create the same level of data, and they're both optimal. So this function had two optimal cases, and that's why they became the same thing. That's my take of this this regression line. But you can just change that to any level you're comfortable with. So let me change it to 5 and see if 5 is statistically significant. Yes, even 5 is statistically significant. So let's change it to 6. Okay, if you add the 6th degree, that means L stat to the power of 6. That will become insignificant. So if you want to keep it, you should keep it up to 5. And you create a large variances here by doing so. Okay, so that was another thing we needed to take into account. So we can add polystat up to any level. And the last thing that is important in the class is how to deal with qualitative predictors. So how to deal with qualitative predictors. As you probably can remember, we were using dummy variables. For each class or each category, we should have n-1 dummy variables. So for this example, I'm going to use the car seat data, which come from the same packages that we have. So let's see what car seats is. Car seats simulate a sale of child car seats for 400 different stores, and it shows the relationship of the sales with the competitor prices, the community income level, the amount of money they spend on advertisement, population of that region, price, and so many other factors. Some of these variables are factor variables. For instance, the education level is definitely a factor variable here. Income is a quantitative variable. That is fine, but some of the other variables we have are factor. For example, shelf lock, which is a factor with level bad, good, and medium. That is definitely a categorical variable, so we should treat it as categorical variable. So in our regression lines, we have to deal with them as categorical variables, and therefore when we have regression line, we should have dummy variables like this. So how do we create dummy variables? One thing cool about R is that if the data is already defined as factor variables in your data frame, you don't need to do anything. It just creates dummy variables for that. But if it's not, then you have to redefine it as factor. So if you have a variable x that is not that is categorical, but is treated as quantitative, you can put it in as factor and just put it back as the x, and that we will automatically make it the factor variable, and then R knows how to deal with that and make dummy variables. In this example, M shelf lock is already defined as categorical variable, so we have easier life with that. So let's see. Let's look at the names that car seat has. Okay, sales. Yeah, it has everything that is defined here in its dictionary. And let's look at the summaries it has. If you look at the summary, you can easily find whether or not you have categorical variables. Yes. So here shelf lock was bad, good, and medium. So that is definitely a categorical variable. Let me look at. Oh, urban is also a categorical variable. US or non-US is also a categorical variable. Education is not treated as categorical variable because that is the amount of years the people studied. That changed from the minimum of 10 years of studying. Oh, they were very educated. up to 18 years of studying. That means you should have at least, I think, master's degree to qualify for that. So that was a quantitative variable. So it wasn't qualitative. So we obviously have 3 categorical variables: shelf lock, urban, no urban, and US. So let's run our regression line here and see what we create. The good thing about this data is that it's already defined as categorical variables. Okay, so our fit 1 will be linear model. You are usually interested in predicting sales, so I just write sales. And then you want to regress it on everything you have, and let's say you want to add some interaction effects. If you want to add interaction effects, if you already have the variables here, you should use columns here. Okay, so let's say you want to have the interaction effect of income and advertising variable, and also you want to have the interaction of age and price. So you should tell R what data you're using. That was car seats. So let's look at the outcome. Oh, what is not? Okay, I think sales was in capital letters. Okay, linear model of sales, income, advertising. Okay, I think that should work now. LM sales, income, advertising, adverse. Okay. Sorry for that. And how about price? Is it yeah, that is capital letter. I don't like this feature because it's capital letter sensitive. Come on. Oh, income. Look how many typos I have. Oh, finally. Okay, so let's see what fit 1 is giving you. Okay, fit 1 gives you all the variables you want, but one thing I want you to remember is that is how it treated the categorical variables you had. So urban, if it's urban, the sales is 0.14. If it's in US, that's the if it's US paid, it's if the store is in the US, the actual sale is lower. Although these two numbers are not significant, but you can see with that insignificant number, it seems like, let's assume it was significant. So let's assume this categorical variable has 3 stars here, meant they were very significant, and the p-value was less than 1%. So let's see how we should have interpreted this value. That would say, if everything else is treated constant, if everything else was treated constant, you would expect that your sales in $1,000 be 0.15, which is $150 on average, less than the sales for non-US retail stores. And for urban, if it was a significant thing, you would say, okay, if the location of a store is in urban areas, you expect that on average you would sell $140 car seat more for the retail stores. Okay. Education was not significant either. So price was significant. Age was how about age was also significant? Okay, this interaction effect is worthless. How about income and advertisement? Yeah, that interaction effect was important. Though the magnitude is small, we should see if we multiply income by advertising and then by this number, we get a large number. And we can see how shelf lock medium and good performed in comparison to bad. So the point I was trying to make was to see how R treats qualitative variables. Okay, well, that was all about linear models. As you can see, it's pretty easy to work with linear models. One thing you should remember is when you're dealing with predictions. I think the hardest part is that you need to define the data you want to have predictions based upon here. The interval and level is not that important. You can just erase it. But But if you're running test and training data, you must put your test data here for the predictions and then compare it with your training data. In my next lecture, when I deal with categorical variables and 3 different methods there, I will show you how you can divide your data into the test and training set and how you can treat that. Thank you very much.